All right, today we're going to talk about a paper that really truly changed the game for computer vision models, Squeeze-and-Excitation Networks. And this wasn't just, a small step forward. This was a completely new way of thinking that basically taught AI a brand new skill, how to focus.
So let's just jump right in with the big question this paper was trying to answer. For the longest time, the path to building better AI seemed pretty straightforward. Just build bigger, deeper, more complicated models. But this paper came along and asked a really brilliant question. What if we could get way better results, not by adding more brute force, but by adding a little more intelligence?
Now, to really appreciate just how revolutionary this was, you got to understand the world it came from. See, back in the mid-2010s, computer vision was basically in the middle of this massive deep learning arms race.
And a strategy back then was super simple. Depth was king. You had VGG nets, which proved that just stacking more and more simple layers could give you incredible performance. Then came Google's inception networks, which were a lot more complex, kind of like building with intricate Lego blocks. And then, of course, ResNets blew the doors wide open with this clever trick called a skip connection that let us train networks that were hundreds, even thousands of layers deep. The message was loud and clear: if you want better performance, just go deeper.
So all these amazing complex models, they were all laser-focused on one thing: capturing these really intricate spatial features in an image. How all the pixels relate to each other. But in this frantic race to stack more and more layers, they were all kind of ignoring another super important dimension of information. Something was definitely missing from the picture.
And that's where this paper comes in, with its core brilliant idea. Instead of just obsessing over spatial relationships, the authors decided to look at something totally different: the relationships between the network's own internal feature channels.
And honestly, this quote from the paper just nails it. They wanted to create something that could adaptively recalibrate channel-wise feature responses. Okay, what does that actually mean? Well, in plain English, they wanted the network itself to learn, on the fly, which of its own internal data streams were the most important for whatever image it was looking at that exact moment.
This whole idea is called channel-wise attention, and it's a really cool concept. Think about it like this. A typical neural network has hundreds of these internal channels, and each one is basically looking for a different thing. One might be a vertical edge detector, another might be looking for the color red, and a third might spot a certain kind of texture. Channel-wise attention gives the network the ability to say to itself, okay, I'm looking at a stop sign. My red detector channel? Yeah, that's absolutely critical. Let's crank that up. The octagon shape detector channel? You bet. Turn that one up too. But my furry texture channel? Probably not going to need that one right now. Let's just turn that one way down. Okay, so that's the what. But what about the how? How do they actually build this clever attention mechanism? They created this small, really elegant, and incredibly powerful module they called the Squeeze-and-Excitation block, or just SE block for short.
Probably the best way to wrap your head around it is with an analogy. Just imagine the network's channels are like all the individual instrument tracks in a song. You've got your drums, your bass, guitar, vocals, all of it. The SE block acts like an expert sound engineer who's trying to get the perfect mix.
It all happens in 3 really simple steps. First up, you've got squeeze. The engineer listens to the whole song together to get a global sense of what's going on. The network does the same thing by squeezing all the information from each channel down into just a single number, giving it a high-level summary. Second, excitation. Based on that overall vibe, the engineer decides which instruments need to stand out. The network uses a tiny little neural network to figure out an important score for every single channel. And finally, scale. This is the easy part. The engineer just pushes the faders up or down on the mixing board. The network simply multiplies each original channel by its new important score. And just like that, it turns the volume up on the useful features and turns it way down on the ones it doesn't need.
And the real genius of this whole thing is just how simple it is to use. The SE block isn't some brand new, complicated architecture you have to build from scratch. Nope. It's this tiny, super lightweight module that you can literally just drop into an existing network like a ResNet. It's like giving your already powerful model a small, clever brain upgrade that makes it so much smarter.
All right, so the idea is super elegant, right? But the million-dollar question is, did it actually work? Well, this is where things get really exciting. Let's look at the proof. This number right here, this pretty much says it all. The CNET architecture didn't just do well, it absolutely crushed it. It took first place at the huge ImageNet competition back in 2017 with a top 5 error rate of just 2.251%. Now that was a 25% relative improvement over the winner from the year before. I mean, that's a massive jump.
But look, winning the competition is only half the story. This table from the paper, this is where the real magic is. You take a standard ResNet 50, you add the SE blocks to it, and boom, the error rate drops like a rock, with basically zero extra computational cost. But here's the kicker. This new, smarter SE ResNet 50 performs almost as well as a ResNet 101, a model that is literally twice as big and needs way more processing power.
And that right there was the mic drop moment. This was the ultimate proof. The Senate proved that being smarter was way more efficient and effective than just being bigger. It completely shattered that old idea that deeper is always better. So yeah, the impact of this paper went way, way beyond just one competition. It really kicked off a revolution in how people design neural networks.
First off, squeeze-and-excitation blocks pretty much made channel attention a fundamental, must-have tool for anybody building computer vision models. The idea was just so powerful and so easy to use that it became a standard part of tons of state-of-the-art models. And maybe the most important legacy, it was a major stepping stone to the much more complex attention mechanisms that you see everywhere today, like in the transformer models that are dominating all of AI. It taught the whole field that being smart about your resources could win the performance arms race.
And that leaves us with a really fascinating thought to chew on. The SE block learns to reweight features inside a single model. So what if you took that same exact idea and just scaled it up? Imagine you have a whole team of different AI models, right? Each one's an expert at something different. What if you used an SE-like mechanism to let the whole system dynamically figure out which expert to listen to for any given problem? You could build this incredible super network that always knows which specialist to trust.
This is for entertainment purposes only.